efficiency. If I do not multiply here with 100, then it is packing fraction. But if I multiply here with 100, then it is packing efficiency. So when it comes efficiency, efficiency is in terms of percentage. While the fraction is what? Fraction only, right?
Yes.
Yeah. So if I multiply fraction with 100, then it gives packing efficiency. Now we
Sir,
have to calculate.
how do you know radius of the atoms? Like, how do you calculate it?
That we have to study. Means in simple cubic unit cell, there is one relation between A and R. I will tell. That's what I have to. We
Sir,
have to study.
what is R?
Wait. That's what I'm explaining now. R is what? Sphere is there, right?
Sir,
Radius.
okay.
Radius of sphere.
Sir, what is R? I mean A.
A is what? Edge length, na?
Okay. My bad. Yes,
That EBC is there. Do you remember?
yes, sir.
And when it comes cubic will have same. A equal
Yes,
to B equal to C. Okay.
yes, sir.
Now look at here how it is calculated. You don't have to calculate in exam. These values are fixed. I have just shown you here. See, packing fraction of simple cubic unit cell. What is the value of n?
1.
1.
So I will put the value of n here 1. This formula I am using, n value is 1. What is the next I have written here?
Volume by one particle.
So can I write down 4 by 3 pi r cube?
Yes, sir.
Below that what I have written?
Volume of unit cell.
A cube I have written, right? So now there is one relation between A and R when it comes to the simple cubic unit cell. And that relation is that A equal to 2R. A equal to 2R. How? From the diagram also you'll understand this. Look at here. This is what the simple cubic unit cell, right? Can I say this is the radius of the sphere?
Yes, sir.
This is also radius of sphere?
Yes, sir.
R. And what is the entire length? This is
2R.
2R. We can say A also, right?
Yes, sir.
Age, na, it is entire. This thing is A, right? Entire length.
Yes, sir.
What is the relation between A and R then?
A is to R.
It's 2R.
So in the same way, we can calculate those relations. Okay. We have to study those for the and not for IP. Directly we can find here. Write down here. So what is the relation here between A and R? What is the relation between A and R for the simple cubic unit? So in place of A, can I put 2R?
Yes, sir.
Yes, sir.
Can I cancel R cube?
Yes, sir.
Then all this calculation I can do. I will get the packing fraction as the 0.533. Okay. So packing efficiency I have to write down in percentage. Then it will be a 53.3%. So this value is fixed. It will not change. Whenever if question comes in exam, what is the packing efficiency or packing fraction of simple cubic unit cell? This is fixed universal value 53.3. Clear this thing?
Yes, sir.
Sir, can you repeat how you got A is equal to 2R?
A equal to 2R, look at here. This is what the simple cubic unit cell structure. Okay, this entire length is how much?
Okay, that is A. Okay, sir.
A, right? Now understand?
Yes.
This is radius, this is also radius, so A equal to 2R. Clear?
Sir, would a formula be different for BCC and FCC?
It will be different. It will not be A equal to 2R because those are not touching, right?
No, sir. I mean the general formula N into volume of particle.
That is fixed. N value will change and that A and R relation will change. I have given here. See here. If this is the packing efficiency, means what? This is the space occupied by atoms or the spheres. Then the remaining space, it is called as void. So what is the volume of empty space or void in case of simple cubic unit cell? 100 minus 53.3, that is 46.7. Clear this thing?
Yes.
Everyone?
Are we supposed to remember these values, sir?
This one you have to, I will tell you how to remember. Very easy it is. All three I will tell first and then I will. Then in BCC, what is the value of N?
2.
2. So that 2 value I will put. Then again 4 by 3 pi r cube divided by A cube, right? When it comes to the BCC, that relation is 4R equal to root 3A. This is the relation between R and A. 4R equal to root 3A. So in place of A, can I put 4r by root 3?
Yes.
Right?
Yes,
Cube.
sir.
So if you solve this one, you will get 68% as the packing efficiency. Clear? And wide will be 32. Then I can calculate same for FCC. You don't have to calculate this now. Don't worry. Okay. Then I have FCC. What is the value of n in case of FCC? 4, right?
4.
Okay. So then that 4 value I can put it here into 4 by 3 pi r cube. Now here relation. What is the relation in case of FCC? Again 4r equal to root 2a. It is easy to remember. See, in previous care, how much it was?
4 hours.
4R
3a.
root
And here how much it is? 4r root 2a.
root 2a.
So even if you solve it here, you will get 74 packing efficiency. Now look at here. All I have written here. When we have SCC, BCC, FCC, 3 only we have initially. Okay. What is the n value? N is number of atoms. How many number of atoms present in SCC?
1.
1. That. How many number of atoms in BCC?
2.
2. And how many number of atoms in FCC?
4.
That I have written. Now coordination number, at this moment you just buy out this one. That coordination number in SCC is 6. In BCC it is 8. And in FCC it is 12. Okay, because it will take a lot of time to study that one. We'll study this thing. Okay. Now packing efficiency value, what will happen in exam? Now you will get MCQ type of, not I'm talking about like advanced one. So how will you remember this thing? Simple. SCC, S is there. You will remember this value actually. 52 or 53, something will be there. Huh? You will remember this value, but you will forget whether 52 or 53 belongs to BCC, SCC or FCC. Whether that 68 belongs to SCC, BCC or FCC. How to remember? Very easy. Look at it. SCC. This is like S is there, right? And in 52 or 53 something will come. 52 only will come, I guess. Huh? So this 52, 5 looks like S. So when it's 52, 5 looks like S, SCC. Okay, next. 68 is there. Now 1 is fixed. Now we got. Okay. Now there is confusion between BCC and FCC, whether 74 is for BCC or FCC. How to remember? In 68 there is 8 is coming. This 8 looks like B, right? Shape is similar, right? So in this way you can remember this value. That 68 is for BCC. If 68 is for BCC, 52, 5 looks like S, it is SCC. Then obviously 74 will be for
Sir,
FCC, right?
FCC.
FCC.
Can you recall now this thing?
sir,
Yes.
I have a question.
Yes.
Sir, is coordination number here like experimentally determined?
Yeah, yes.
Sir, then how do you have valency of 12
Which valency of 12?
like in FCC?
That is not the valency. It's like how many surrounding atoms are present.
Okay.
We'll study that. Don't worry. I will explain this thing. I did initial one PDF I have sent to you, no, solid state. In that I have shown with different colors. White is 12 and all. I will explain that.
Okay, sir.
In that it is given to find out this coordination number and all.
Sir, can
Here
you tell
is-
how you remember that again? Means?
Which one?
Like how you remember the percentage values?
See, SCC S looks like 5, 52. Now there is confusion between BC and FCC whether 74 belongs to BCC or FCC, right? Now in 68, 8 comes which looks like B. So 68 belongs to BCC. Then obviously 74 will be for FCC.
Okay.
Okay. Now there is one question here that you have for the density. Do you know what is the formula of density? Simple. Mass of unit
volume.
divided. What happened?
Yes, sir. Mass by volume.
Mass of unit cell divided by volume of unit cell. No need for this one. Like this proof is there actually. How we got this last formula. At this moment, you just have to remember this last formula. This is the proof to get the formula, like last one. What is the formula? Nm into Na cube. Nm into Na cube. What this N stands for? It stands for number of atoms or the pairs. How many are in SCC?
One,
BCC
two,
and FCC?
4.
4.
Okay. Na stands for Avogadro number. A you know edge length. So only this formula you have to remember, not require this derivation. Okay, it comes like this is the proof how it comes here at this moment. So Na Nm into Na cube. Okay, all this you know edge length, or it is also called a lattice parameter. Nm is what? Molar mass. Clear till this point? You
Yes,
just have
sir.
one straightforward numerical here, I guess. Okay, they have provided this value. One you have to calculate from here. Okay, and then you have voids or interspatial or holes in the crystal. Simple thing. Let's suppose you everyone might have seen cricket ball, right? If you keep three cricket ball in your hand, there will be some space at the center. If you put horizontally all three cricket balls in your hand, it's like this one, there will be some space here at the center.
Yes, sir.
Okay,
Yes.
Yes.
and on that center if you keep one more ball, still in between there is some little bit space will be there, right, from inside.
Yes,
Yes.
sir.
That space is called as tetrahedral void. Why? Because how many atoms are involved to create that space or void?
3.
Four.
Three. One,
Sorry,
three,
sir. 4,
three
4, 4.
horizontally, one at the top. It looks like tetrahedral shape, right?
Yes,
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 sir.
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 That's why it is called as tetrahedral void. Clear? That shape of void is not tetrahedral. When we arrange the atoms, at that time arrangement becomes like tetrahedral shape. I'm not saying that the shape of that space or void is tetrahedral. I'm saying how the atoms are arranged. When atoms are arranged in tetrahedral way, some space is created at the center, and that space is called as tetrahedral void. Are you understanding?
Yes.
Yes, sir.
Okay. Clear this thing, tetrahedral void. So
Yes,
the
sir.
vacant space between four touching sphere, three at the bottom, one you keep on from the top. It's like three will be there. At center there will be some space. On top you keep one more. Still there will be that space, right? Still there will be some space. That space is called as tetrahedral void. Clear this thing?
Yes, sir.
Okay. That only theory part I have written here, like how we are getting it. Okay. Now, if any atom, if I keep in a tetrahedral void, what will the coordination number of that atom? 4, right?
Four.
Because that space is surrounded by how many atoms?
Four atoms.
4.
4.
Then comes the octahedral void. Now, how you have to do? 3 at the bottom, 3 from the top. If you keep them, still there will be some space. See, 3, you put it like this, 3 balls on the horizontal surface, right? 1, 2, 3. There will be some space. From the top also, you take one 3 balls like this, and this 3 you keep it here on this one. Still there will be some space, right, in between, like here. We can keep the arrangement like this. Bottom, let's suppose these blue ones are the bottom 3. There is some space here. From the top again you keep it 3 in this way. Still there will be some space left here, right?
Yes,
Okay.
sir.
Yes,
Yes,
sir.
sir.
Yes.
This is called as octahedral void. Okay, because this space is created when 6 pair or atoms we arrange. That's why it is called as octahedral void. Clear this thing?
Yes.
Yes, sir.
How
Yes.
many atoms are required to create the tetrahedral void?
4.
4.
6.
And how many tetrahedral?
Tetrahedral. Four.
And how many atoms are required to create the octahedral void?
6.
And now you understand this one. Now it is very easy to calculate how much void will be there. Simple. Do you know what is the n value in SCC?
1.
What is the n value in BCC?
2.
2.
2.
What is the n value in FCC?
4.
4.
You know this thing, everything will be sorted. Look at here now. Number of octahedral void will be equal to number of atom, that n value. So if someone asks how many octahedral voids are present in FCC, what is the answer?
Four.
4.
4.
How many octahedral voids are present in BCC?
2.
2.
How many octahedral voids are present in FCC? SCC?
1.
1.
One.
And how we calculate number of tetrahedral void? 2 into octahedral void. So if someone asks how many tetrahedral voids are present in FCC, what is the answer?
8.
Eight.
first 2 into octahedral void. So how many octahedral void is there in FCC? That is n value. What is the value of n for the FCC? 4.
Four.
So
4,
octahedral void will be 4 and tetrahedral void will be.
Eight.
8.
Clear this thing?
Yes, sir.
Yes,
Forget
yes.
about this one last, not required now. Just this, how to calculate, that is important. Understand this now?
Yes,
Okay.
sir.
The same thing, that calculation. Number of octahedral void in SCC 1, BCC 2, FCC 4. Number of tetrahedral void in SCC 2, BCC 4, FCC 8. Twice of this one, multiplied by 2. And the third thing is what? Means important thing from here, defects or imperfection in solid. Now look at here. What is the defect or imperfection? Any irregularity in arrangement of particle is called a defect. Simple. A B A B B A B A B A B. Proper arrangement is there. Means here A B A B pattern is followed. Here B A B A pattern is followed. Here again A B A B is followed. But if you see here A B A B, okay, pattern is there. B O, some atom is missing here. Just a vacant space is there. Then again B A A B A B. So here it is regular or perfect crystal, but when it comes to here, as the atoms are missing, then it is irregular crystal, which is called as, also called as defects. Clear? What is the defects or imperfection in solid means what? Atoms will be missing. If we expected atoms on their regular positions, but they are missing from that position. Those are called as defects. Clear?
Sir, how is the
Yes.
bond formed without the atom?
Which bond?
The one which is missing in that irregular
So
crystal.
this one atom will be there, another atom will be there. There will be some force present between them. So this is not a bond. Huh? Don't think this is bond. I have shown the arrangement. This purple one is not a bond. Okay, I
Okay,
just
sir.
for the proper arrangement means to have the in proper way. I have shown this one. Clear?
Yes,
Don't
sir.
think that this is bond. There is no atom. Then how bond is formed? No, this is not a bond. Okay, it's like from B, like one atom is missing. Some space is created in it, like that.
Okay.
Now these defects are actually of two types. Now look at here. Here only one atom is missing here. Such type of defects are called as point defect. That there is irregularity in the atoms at only one particular point. But when it comes to here, look at here. There is irregularity at this point, at this point, and at this point. If I join all those points, it's like there is irregularity in about line. So this is called as line defects. Perfect
Sir,
line
how does this happen?
means one.
Like, either how do defects come about? How do they happen?
Like if those uh, they have A and B, there is some forces will be there. So when we increase temperature more than their melting point and all, it's like the force of attraction between them can break down. So those can jump outside, like that. We can have those such type of defects, or
Then
we
why
can
does line defect happen?
what
Why does line defect happen? Like,
see defects is very important actually. You might have studied the semiconductors in physics.
yes, sir.
You
Yes,
might have
sir.
studied doping and all.
Yes, sir.
We can increase the efficiency of semiconductors by creating this type of means we can remove the atoms and we can fill another atom there. You might have seen, you might have studied those N-type, P-type semiconductors, right?
Yes,
Yes,
sir.
sir.
This thing, it is there in this chapter also for IP for you. Okay. So like we can remove actually also by like artificially, and we can put another atom to increase the efficiency. Okay. So when we have atom missing it only at one particular center, then it is called as point defect. Means what? Irregularity about point. Line defect means what? Irregularity about line. See here, entire line, there is atom missing. Understand? So defects are classified into how many categories?
Two categories.
Which two categories?
Point
Point
and line defect.
line.
Defect and line defect. Now this point defect we have to study again in detail. Point defect further classified as stoichiometric defect and non-stoichiometric defect. What is the difference between them? In case of stoichiometric defect, there is no change in the stoichiometry of compound. It's like that perfect integer will be there. NaCl 1 1, MgCl 2 1 2. Perfect will be there, right? In case of non-stoichiometric, that stoichiometry changes. Means like if NaCl is there, na, I am giving example, hypothetical. Then it Na will be like 0.90 and Cl1. Like that, it will not be a perfect integer. So there that stoichiometry changes. Why? We are removing atoms here, na. So obviously number of atoms will change. So Na will not be a 1 then, so it will be less than 1. So like that it is. Now this stoichiometric defect, there are two examples of stoichiometric defect. One is Schottky defect, another one is Frankel defect. We have these two for the IP. And non-stoichiometric defect, again two types are there: metal excess and metal deficiency. Okay. Now what is this thing? This Schottky and Frankel, that we'll study now. Simple thing. What is the Schottky defect? Read the first point, anyone. Read.
This type of effect is produced when one cation and anion are missing from their respective positions, leaving behind a pair of holes.
Pair of holes. One cation and one anion are missing. Right? If one cation and one anion is missing, you tell me one thing. Is there anything will happen? Is there any charge will come on that material?
No, sir.
No,
So can I say that electric neutrality will be maintained?
yes.
Yes.
Yes,
Okay.
sir.
One more thing. See, all these points are interlinked. So first, what is that? In this type of defect, one atom and one cation and one anion are missing. Okay, from their respective position. Okay, one thing is there. It's like this thing only. We are studying point defect, no? So one cation and one anion is missing. You tell me, will anything will happen to the volume of that entire crystal? Will the volume
Yeah.
decrease?
Yes, sir.
Huh? See, I'm saying that from here, let's suppose from here I remove the B. I am removing again A here. Is anything is happening to the volume?
Volume is
I have made it here small, this one. No, right? It is like this one only. So anything is happening to the volume.
sir, but then there's an empty space there, no?
Changes,
So
right, sir?
space will be there, means void will be there, no? But total volume of that unit cell. More void created, that I understand. I'm asking total volume of unit cell. Will it decreases?
Sir, why won't it decrease?
Huh?
Wonderworld first also, right? To like attract it.
This is what the entire crystal is there initially. I removed one atom. It's like entire classroom is there. Okay. I removed one person. So entire volume of unit cell decreases. Or let's say I removed 2% from the class. Let's suppose you went out of the class. Okay. Now entire volume of unit cell, entire volume of that class decreases.
Okay, no, it won't.
And same, right? So if I remove two people, entire volume of the class will remain same or it will decrease.
It'll remain same.
Okay. Now one more thing. If volume is remaining same, what will happen to the density?
It'll decrease because mass change.
See, density will decrease. Why? Because as I have removed the atoms, each atom will contribute to the mass, right? Means if I
Yes.
remove the atoms, mass will decrease. Volume is remaining same. What will happen to the density?
It decreases.
Density will decrease. So we got 3 points. What is the first point about the Schottky defect? That in this defect, one cation and one anion will be missed from its original position. Okay, one cation and one anion will be missing. First point. What is the second point? What will happen to the charge electrical neutrality?
There's
It is
neutral charge.
What will happen to the
It'll remain
electrical
neutral.
neutrality? Huh?
It's
So it'll
neutral.
remain neutral.
It will remain neutral only, right? Second thing. Now third thing, what will happen to the density?
Density
decrease.
decreases.
Look at it. So just have to remember 4-5 points about this one. Okay, density decreases, electrical neutrality will be maintained. Now one more thing, as cation and anion both are missing, it is possible only if both of them have almost similar size. If cation and anion both will have almost similar size, only then one cation and one anion both we can remove from there. Okay, this is also one point. Now don't worry about this. What is this radius ratio and all? Okay, if I am saying cation and anion has similar size, radius ratio is nothing but radius of cation divided by radius of anion. If they have almost similar size, radius ratio will be what?
One.
close to the
Almost.
unity 1, that's what we are written. Not far below unity means what? It is similar, close to the 1. So when the Schottky defect is possible, when radius ratio is close to 1. Or I can say in other way, when the size of cation and anions are almost similar. Clear?
Sir,
Yes.
why should they be
Which
similar?
one? See, we are removing one cation and one anion, right?
Yes,
Both need to be have same size or charges so that that electrical neutrality will also be maintained.
but sir, if it has different size but same charge, neutrality will still be
But if
maintained.
see, it's like if we it's like from that radius ratio, na, many things will come actually, like which atoms are present and all. So it depends on that factor actually. Directly, it's difficult to explain without that radius ratio. It's like it will give information about the like how which type of voids are there and all. From there we got that idea.
Okay, sir.
So now what are the 3 4 points that you have to remember in Schottky defect? First one, it is observed when one cation and one anion is missing. First point. Second point, what will happen to the electrical neutrality? It will be maintained. What about the density?
It decreases
And what about the when it is possible? When the size of
when
cation
radius
and anion is
close to unity.
okay. Now one more thing. As we are removing one cation and one anion, so voids are creating. If more voids are there, obviously the stability of crystal will decrease then, because more voids are creating in between. So there is high chances that that structure can fall down, it can break. See, if we have a wall there, if we remove some bricks from the wall, there is chances that that wall will be collapse, right?
Yeah.
That's what the meaning here. Okay, that stability of crystal will decreases. Understand this one? And you can have examples: NaCl, CSCl, KCl, KBr, like that. Almost they have similar size. Clear this thing? Clear
Yes,
short
sir.
effect?
Yes,
Okay. Can you tell me 4 5 points without seeing it? First point.
electrical neutrality is maintained.
Okay. Second point. Hey, first
Density is decreased.
where it is
Cation and
observed, that is
anion.
first point.
One cation and anion are removed.
Okay. Second one,
Electrical neutrality.
electrical neutrality will be maintained. Third point.
Density
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 decreases.
is decreased.
Fourth one.
Size of
Size of
cation and anion are almost same.
Okay. Fifth one. Example.
NaCl, CSCl,
KCl and all.
ACl,
KVR.
KBr
Okay. What will happen to the stability of crystal?
decreases due to larger void.
Right? It's like if you remove some bricks from your wall, there is high chance that it will collapse, right? Same thing. Clear? So this is what the Schottky defect. Look at here. One cation, one anion is missing. So Schottky defect. Now what about the Frankel defect? One thing will be missing from here, but it will not goes outside the crystal. It will stay in the voids which is already present in the crystal. It's like it is removed from here, but it is present inside the crystal only where voids are there. It's like initially we are removing two people from the class, right? Now we are removing the two people and we are asking them to sit down on the ground. They are present. They will be present there only. They will not go out of the class. Understand this one?
That can be an anion or cation, right?
Ah, it can be anything.
Okay.
Okay. Clear this thing? Now you tell me what will happen to the density then?
remains
It will
same.
Remains
remain the same.
constant.
Density will remain same. Okay. Understand this one? And now
So
when
sir,
yes.
this defect can occur only when one atom leaves or multiple can also leave.
No, only basically one atom can leave, second can also leave, but it should present here only. It should not go outside the crystal.
Okay.
Okay. And now the no, Schottky defect, when it is possible, when the size of cation and anions are same. When the Frankel is possible, when there is a difference in the size of cation and anion. It's like opposite one. If we study in comparison, you will able to recall it, remember it. So first one, in short key, what happens? One cation and one anion will be missing from their sides. First one. What about Frankel? One cation or anion will be missing and it occupies the interstitial side. This free space is called as interstitial sides. Clear? Second thing, when we have short key defect, short key defect is possible when size of cation and anions are same. When the Frankel defect is possible,
When there's a difference in the size
When
of
the
cation and
when
Size is not same.
okay, there is gap between the size or difference between the size. Third thing, what about density?
density remains same in Frankel but decreases in short key defect.
In short key, density will decrease, but in Frankel, it will remain.
Same.
Same.
Clear this thing? Okay.
Yes.
Yes, sir.
So these are only points are there. Okay.
Sir,
Uh,
sir, can Schottky and Frankel defects occur at the same time?
yeah, it can AGBR. It show
Oh,
both.
oh, okay.
Okay. Clear this thing. So four differences you should know that I have given here also. Okay. An example you can remember ZNS, AGCL, AGBR. You can write down that AGBR here also in case of short key. Clear. This question you have for 4 marks, defects. You just have to write down 3, 4 point in every case. Short key defect 3, 4 point. Frankel defect 3, 4 point. Can you write down now?
Yes, sir.
Okay. Now this one question is there. Read this question.
If
Read this.
NaCl is doped with 10 power minus 3 mole percent SrCl2,
Hmm.
what is the number of cationic vacancies produced?
Now look at it. Doping means what? Adding impurity. What is given? 10 to the power minus 3 mole percentage. 10 to the power minus 3 mole percentage how much? Can I write down 10 to the power minus 5 mole of SrCl2? Percentage means what? We can multiply with 100 that. Sorry, divide by 100. Sorry. Divide by 100. Percentage
Yes.
means we can divide by 100, right?
Right.
So that is what 10 to the power minus 5 mole SrCl2. They are saying in this SrCl2 they have added NaCl. Okay. And they are asking what is the number of cationic vacancies produces. Simple thing. How the SrCl2 will dissociate Sr2 plus and 2Cl minus. So what is the charge on Sr?
+2.
And what is the charge on single Na?
+1.
+1.
So now see, this is what one thing is confirmed when we are doing all this doping and all, that electrical neutrality is always maintained. So you tell me, initially I have NaCl crystal. In that NaCl crystal, I have to add Sr2 plus. Then how many Na I have to remove?
2.
2, sir.
2 Na I have to remove, because when I remove 2 Na, only then I can remove +2 charge, because I am adding +2 charge and I have to maintain electrical neutrality. Clear? So how many Na I have to remove?
2.
2.
2. When I will add one Sr2 plus, 2 Na are removed. Now look at it. I removed one from here. This one I can make it. Wait 1 minute. I removed one from here Na, and I removed one from here. Okay, 2 I have removed. But how many Sr we have added? Only one, right? So when we are adding one Sr, one cationic vacancy is created. Yes or no?
Yes, sir.
One cationic vacancy is created, right? One Sr2 plus replace 2 Na plus to maintain electrical neutrality. But one lattice side will remain vacant only. One is vacant here. Are you
Yes, sir.
understanding? Okay.
Yes, sir.
Can I say for every Sr2 plus ion, one cationic vacancy will form? Whenever I
Yes,
will
sir.
add one Sr2 plus, every time I will get one free space. Because whenever I will add one Sr2 plus, I will remove 2 Na plus. And in place of one Na plus, I can put Sr. But still one space will be vacant. So whenever I am adding one Sr2 plus, one vacancy will create. Are you understanding?
Yes, sir.
Yes,
Yes,
sir.
sir.
So how many Sr plus ions are there? Moles I have. Moles I have.
Avogadro's
Right?
number.
Can I get number of ions from the moles?
Yes, sir.
That's the
Into
formula.
Avogadro.
So can I do this one? So number of Sr plus ion 10 to the power minus 5 Na. This much only vacancy will create, Nare.
Yeah, sir.
Clear this thing, so you'll get this answer. Okay, if you solve this one. Okay, clear?
Yes, sir.
Yes, sir.
Yes.
In your that material, it is given like this. You can follow anything. Which one you find it suitable? Either this one or this one. Anything, no problem. Clear? And one more question is here like this. No, simple. You read the question. Same to same question is there for the board. Same this question. Read this one.
The composition of iron oxide is Fe 0.930.
Okay.
The
0.93. Stoichiometric defect or non-stoichiometric?
Non-stoichiometric.
Non-stoichiometric. Now look at here. Which one is more? Fe is more or oxygen is more? What is the amount of Fe atoms? 0.93. What is the oxygen?
1.
1. Who is more?
Oxygen.
oxygen
Who is less?
iron.
Whose atoms are more? Oxygen are more. That is one. Whose atoms are less? Iron. So iron is what? Metal here. So herein we have written, when there are non-stoichiometric defect, there are two types. One is metal excess, one is metal deficiency. Now here we have non-stoichiometric. Okay. From that, which one it is? Metal excess or metal deficiency?
Deficiency.
The number of metal atoms is less than number of non-metal. So it is metal deficiency. And in every defect, remember one thing: electrical neutrality maintain. Okay. So consider Fe 0.93 are there. They are what? What is the question they are asking? How many Fe3 plus are possible? Percentage of iron in the form of Fe3 plus. There can be Fe2 plus also. There can be Fe3 plus also. They are asking how many percentage of Fe3 plus are there. Okay. How will calculate this one? Fe 0.93 contain 2 plus as well as 3 plus. Let's suppose 3 plus are X. Then how many Fe2 plus will be there? Total is 0.93. If 3 plus are X, 2 plus will be 93 minus. Okay. One thing. Again, in defect, metal deficiency or whichever type of defect is there, electrical neutrality maintain. So total positive charge will be equal to total negative charge. Yes or no? Now look at here. Negative charge. Who will give negative charge? Metal will give or non-metal will give? Who will give negative
Non-metal.
charge?
Non-metal.
Oxygen will give non-metal. What is the negative charge on each single oxygen atom?
-2.
-2. So total negative charge is -2. Now we have to calculate total positive charge. Now you see here, Fe3 plus is also there, Fe2 plus is also there. How many atoms are there which have 3 plus charge? X atoms are there. How many atoms are there which has +2 charge? This one atom, right? So we will do like this. Total +2 charge is how much? +2 charge multiplied with how many atoms are there? Plus +3 charge multiplied how many +3 atoms are there? Do you understand this?
Yes, sir.
Yes.
Yes, sir.
Total minus charge, how we calculated? -2 charge. How many atoms are there? Only
One
one
oxygen.
oxygen atom, right? So 1. So we are doing this. From here, we'll get the value of X. X stands for what? Number of Fe3 plus. Are you understanding?
Yes, sir.
So
Yes,
yes,
sir.
sir.
Get X atom. Total is how much? 0.93. X divided by 0.93 into 100. We'll get percentage of Fe3 plus. Do you understand this?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Clear this thing? This question? This is there for IPA. Okay. Then this type. I think you might have studied this one. Are paramagnetic, diamagnetic, ferro, anti-ferro.
Yes.
So from definition we'll understand. The last important thing we'll do. That is the Bragg's equation. Okay. Now what is the use of Bragg's equation? It is used to measure interplanar or interlayer distance in solid. Like when we have solids, it is arranged in the layers will be there. Like first layer will be there. Then there will be second layer. There will be third layer. Like layers will be there in solid. Now what is the use of this Bragg's equation? It is used to find out how much distance is present between two layers. What is the distance between these two layers? It is used to calculate that. Okay. I think you might have studied this in physics also, na? Have you studied?
Yes, sir. Yes, sir. But then we didn't go in detail though.
Okay, no problem. Now look at here. I am putting here one line at the center. Okay. Now let's suppose there are X-rays are there. We are inserting X-rays on this solid. Okay. This gap is what? Distance between two layers. And that gap is D. And our aim or the Bragg's equation is actually used to find out this D value only. Okay. Interlayer distance. What is this? D stands for interlayer distance. Okay. Now here X-rays we are inserting on this solid. Okay, so X-rays are falling here. So X-ray is coming from here also, like similar rays we are coming here. X-rays. They will deviate from here, they will reflect and they will reflect like this. Okay. So they are coming from here. Okay. So can I say this is my angle of incidence of X-ray?
Yes, sir.
So angle of reflection will also be the same.
Sir, angle of reflection should be between the normal and the
Which one?
So it'll be with the normal, but
surface.
yeah, it's the same.
Oh, this one will study prior, right? Okay, we can now here. Can I write down the same thing here for the second one also? Like this? Okay. Now here,
Yes.
one more thing. I am taking one perpendicular here. Here also same thing. Okay. Now here, can you tell me what is this angle will be? What will this angle?
So theta only.
I have made the little bit this one. Huh? This will be theta only, right?
Yes, sir.
Okay. It will be like I have to make it like proper way here. This one shifted here. Proper perpendicular here. We'll try. Like proper this way. Okay. So this will be theta only. Okay. Now here. We'll write down some names here. Okay. Let's say this is O point. This is A point. This is B point. Okay. Now here. This is first layer. This is second layer of that solid surface. Okay. Now for a reflected ray to be in the same phase, what is the part difference needs to be? For the reflected rays to be in the same phase, part difference needs to be
N lambda.
okay. So can I write down here for the reflected ray to be in same line, part difference should be
Multiples of lambda.
multiples of lambda. So can I write down n lambda where n can be 1, 2, 3, right? Okay, clear this thing till
Yes,
this
sir.
point is clear.
Yes.
Yeah, now one more thing. Let's come to the this part triangle OAB. Okay, so now in triangle OAB. Okay, now sine theta. What will the sine theta here? OAB. Sine theta, how we write?
AB by
AB
AB by
OB.
opposite side by hypotenuse. AB divided by OB. What is the value of AB? Let's suppose AB value we consider that x delta x is there. Okay, here we consider delta x value is there. What is the value of OB?
B.
OB value. OB. D.
D, sir.
Can I write down here the delta X divided by D? This is what we are getting. So what is the delta X then? D sine theta. Okay. So this is what the part difference, right? For this one thing. So what is the net path difference? Total part difference is how
2
much?
into D sin.
Huh?
2 into D sin.
So net or total part difference will be how much? See here, part difference. How much extra this ray is traveling? This much amount, right? If I compared first ray of X-ray and second ray, how much the second one is extra traveling? This delta X in this incident part. But total how much is traveling? Delta X here and delta X here.
Yes.
So net part difference is how much?
2D sin.
Delta X.
2 delta X. Right? So can I write down here 2 delta X is there. Delta X value is how much?
D sine.
So 2D sine theta. And for the reflected ray to be in the same line, total or net part difference will be equal to n lambda. So can I write down this? This will be nothing but n lambda.
Yes.
Do you understanding this one?
Yes, sir.
Yes.
So what is the equation, that Bragg's equation? 2D sine theta will be equal to n lambda. This is called as Bragg's equation. Okay. And this question is coming from solid state every year. Every year. You go and check previous year papers. Okay. Every year there will be one question for 4 marks. State Bragg's law. Okay. So this equation is called as what? This equation is called as what? Bragg's law, right? Bragg's equation. What is the D? Distance between layers or
Layers.
interplanar distance. Okay, interlayer distance or interplanar. What is the theta? Angle of incidence or reflection. Okay, and then what is the lambda?
Wavelength.
Wavelength of
Wavelength.
X-ray.
Wavelength of X-ray, and that n stands for, actually here we consider order of reflection. Okay, first order, second order, like that. Okay, if someone says first order reflection is there, then n value is 1. Second order means n value is 2. Clear this thing?
Yes, sir.
Okay, so this is about the solid state. Do you understand this one? So from this chapter, what are the important things? Most important is Bragg's law. Okay, and second thing which is more important after Bragg's law is the defects, Schottky and the another one, Frankel defect. Four points actually, at least you should able to remember. Clear this thing?
Yes, sir.
And
There
number
were some semiconductor questions also.
semiconductor, you might have studied this one, that N type, P type semiconductor and all.
Yes, sir.
That's what I have not taken here. I think it is there in physics directly, yeah, the doping and all.
Yeah.
Extrinsic semiconductor, intrinsic semiconductor. Okay. Clear this thing?
Yes.
Yes, sir.
I will send this PDF to you. Okay. You can leave. Now, one more is remaining, right? That catalyst and all. Catalysis, colloids and all. Whenever during your exam, whenever, I think before physics there is time, na? Whenever you have extra time, na? In one day I will take that part. Clear?
Okay, sir.
Okay. Whenever there is
Okay,
more
sir.
gap between two exams, at that time I will take that part also. Do you understand this one?
Yes, sir.
Yes, sir.
Clear this one?
Yes.
Okay.
Sir,
Yes.
so can you repeat the starting question? The
What?
super.
What?
So
What is
starting point, can you repeat again?
which starting point?
So the starting of the class, the super cooling.
This one.
No, sir. The super cool. I forgot.
This one. See,
Yes, sir,
like
the repeating.
amorphous solid, it is, they are also called a super cooled liquid. Means what? Generally, they want to stay in the liquid. Like they, if we are calling them as solid because at normal room temperature, that liquid converts to solid format actually. It's like glass and all are there, right? If you keep the glass for longer duration, that the bottom side thickness of glass will increase. Longer duration means what? It's almost some 15, 20, 25 years. It means what? They are flowing. Okay, that's what they are called as amorphous liquid. Glass is the example of amorphous liquid.
Okay.
Okay, sir.
Clear
Sir,
this?
can you also tell differences again between crystalline and amorphous?
See, crystalline will have regular shape, amorphous irregular. Crystalline, sharp melting point, amorphous, that melting point will not be a sharp. It like range will be there. Crystalline are called as true solid, while the amorphous are pseudo solid or super cooled liquid. Then next come crystalline are anisotropic in nature. Anisotropic means what? Their properties are direction dependent, while the amorphous are isotropic, direction independent properties. Okay. Then next comes crystalline. If you see the crystalline, that arrangement is proper, like A B continuous is there. So that is long range order. While the amorphous will have short means you see here. When we have the crystalline, continuous arrangement is there, A B for the longer duration. But in case of amorphous, AB and again BA means what? That the order pattern is what AB, but it is not, it breaks here. BA comes. So it is not followed for the long duration. So amorphous, they have short range order. Okay. The next is what? Crystalline, we say that true solid, and this is what? Pseudo or fake. Pseudo means what? Fake or super cooled liquid. Density, crystalline will have more density while the amorphous will have less. And the example you can remember. It's like ice, NaCl, diamond. They are the example of crystalline solid. While the plastic, rubber, tire, they are the example of amorphous one. Clear?
Sir, what do you mean by sharp melting?
Sharp melting point means what? If NaCl is there, like water is there, right?
Yes.
Boiling point is like sharp, 100, melting point 0 sharp. If you
Fixed
start the
values.
fixed values, if you try to melt the plastic, do you know at which temperature it will start melting?
No,
Do you
sir.
have that any fixed temperature for plastic?
No, sir.
No, right? That's what they have, the range of melting point.
Okay.
Clear?
Sir, aristotropic, can you repeat again?
Anisotropic means, look at here. When I'm moving in this direction, the order is same. B A order is same. Okay. So when I'm moving in this direction, any physical property will remain same or will it change?
It will remain same.
It will remain same. Now if I change the direction, now see here, what is the order here? A. The physical properties here for the entire direction will again remain same. Means
Yes.
here if it is 80, there is high chances that here it will be different. But for the entire direction, it will remain same, right?
Yes.
Okay, so that's means physical properties are direction dependent. If this direction I am taking, some different physical property. If I am taking this direction, different physical property. So they are direction dependent. That is anisotropic. Direction dependent anisotropic.
Okay.
Clear?
Understood.